Hello viewers, how are you? Welcome to my channel Physics with Ramses. So today we are going to discuss about the time period of a satellite, and we are going to discuss about angular momentum of the satellite, and we are going to deal with the energy of the satellite, as well as we are going to discuss about geostationary satellites and polar satellites. So before going to start this topic, those who are new to my channel, please subscribe my channel so that you will get notifications regarding my channel. And stay tuned to my channel on every Thursday. Why? Because we will release a new video on every Thursday. So don't forget to stay tuned to my channel. Let's start this topic, time period of a satellite. So in order to represent the time period of a satellite, here we consider a planet. Either it might be Earth or any other planet with radius capital. Now we consider a satellite which is revolving around this planet at a height h. Now here the total distance from the center of the planet is represented as a small r, where small r is equals to capital R plus small h. Small r equals capital R plus small h. Now when this satellite is revolving around the planet with a speed v0 around the planet, so the time period of this satellite is represented as 2 pi r by v0. 2 pi r by v0, where v0 is the orbital speed, r is the distance of the satellite from the center of the planet. Distance of the satellite from the center of the planet. Now let's square this equation. As we square here, we get 2 t square is equals to 4 pi square r square by v0 square. v0 square, where v0 is the orbital size speed of the satellite, and we know that v0 is equals to under root of capital G, capital M by R. Capital G, capital M by R, where G is a universal gravitational constant, M is mass of the planet, and R is the distance of the satellite from the center of the planet. So here, as we substitute this value in this expression here, then t square can be represented as t square equals to 4 pi square r square by, and squaring this expression here, we can represent it as v0 square equals to G capital M by R. So in the place of v0 square, we can substitute G M by R. As we substitute, observe that G M by R. This R comes out. R square into R, R cube. Then observe that t square is equal to 4 pi square by G capital M into R cube. Observe that 4 is a constant, and pi square value is also a constant, and G is a gravitational constant, universal gravitational constant. M is mass of the planet, it is not going to change. So if we consider this 4 pi square by Gm as a constant, we can represent that t square is directly proportional to R cube. Based on this expression, we can represent that as the square of time period of a satellite around a planet is directly proportional to cube of the distance of the satellite from the center of the planet. So based on this expression here, we have to represent the conditions for this time period of the satellite. So represent the height of the satellite from the surface of the planet based on this time period expression. Observe that t square is equals to 4 pi square by Gm into R cube. But we know that R is equals to small r equals to capital R plus capital H. Small h. T square is equals to 4 pi square by Gm into R plus H whole cube. In the place of small r, we had substituted capital R plus small h. So we require the value of h in terms of time, height of the satellite in terms of time period. For that, what we are going to do is, we are going to bring this value towards this side. As we bring this here, observe that R plus h whole cube is equals to G m by 4 pi square into t square. 4 pi square into t square. Let's apply cube root on both sides. So I apply cube root, r plus h is equals to 3 by 3, nothing but 1. G m by 4 pi square whole to the power of 1 by 3 into t to the power of 2 by 3. Because time period is a square to the power of 1 by 3. 1 by 3 can be represented as 2 by 3. Why? Because t is having a square. Now from this we have to represent the time period expression in terms of height. So height of the satellite h is equals to g m by 4 pi square whole to the power of 1 by 3 into t to the power of 2 by 3 minus r. Because we brought this r towards this side, plus converts into minus. This shows the expression for height of the satellite in terms of time period, where r is the radius of the planet. In order to get the time period of the satellite as 24 hours, means the satellite has to revolve around the planet in 24 hours. If we consider this planet as Earth, if we consider it as Earth, means the satellite has to cover around the Earth in 24 hours. Means we have to place the satellite at a height of 36,000 kilometers. If you place at this height, then this satellite, it takes 24 hours to complete one revolution around the Earth. And if we place the satellite very near to Earth, means as compared to radius of the Earth, height of the satellite is negligible. Height of the satellite is negligible. So from this condition, observe this expression, t square is equals to 4 pi square by gm into r plus h whole cube. We know the radius of the Earth as 6,400 kilometers. If you consider the satellite is placed at a height of 100 kilometers, as compared to 6,400, 100 is negligible. Then what we can do is we just replace r plus h with r. We replace r plus h with the r. Then a time period expression can be represented as a t square equals to 4 pi square by gm into r cube. Why? Because h is very much less than r. Nothing but r is very much greater than h. So we can neglect h. Then observe that you know the relation between small g and capital G. Small g equals to capital G, capital M by r square. Then g r square is equals to g into capital. So in the place of g capital M, we can substitute g r square. As we substitute the time period expression, t square can be represented as a 4 pi square by g r square into r cube. R square gets cancelled. Remaining is r. Then time period can be given as a t square equals to 4 pi square into r by g. Apply square root on both sides. As we apply square root on both sides, then time period can be given as a t is equals to 4 pi square. Under root of 4 pi square is nothing but 2 pi. 2 pi into under root of r by g. So this represents the expression for time period for a satellite which is revolving around the Earth. So as we represent the height of the satellite is very much less. If we substitute the values of radius of the Earth and g value in this expression, the minimum time period can be given as t is equals to 84.6 minutes. 84.6 minutes. Within this time, the satellite can complete one revolution around the Earth. Take a screenshot. We will continue. So now we are going to discuss about angular momentum of a satellite. So before going to here, we are going to represent the time period expression in terms of density. Why? Because we know that a time period is given as a t is equals to under root of 4 pi square r square by under gm. Now here, where m is the mass of the planet, and we know the relation between small g and capital G as a small g equals to capital G capital M by r square, and we have to represent the expression in terms of density. So for that, what we do is we just consider mass, where we know that mass equals density into volume of the planet, where volume of the planet is represented as 4 by 3 pi r cube, 4 by 3 pi r cube into rho. So as we substitute this value in this expression, the time period is given as t is equals to under root of 4 pi square r square by g into 4 pi by 3 into r cube rho. R cube into rho. Observe that here 4 pi gets cancelled and 3 comes upwards. Then time period is given as t is equals to under root of 3 pi. Observe that here r square gets cancelled. So we have 3 pi by g r rho. 3 pi by gr. So this represents the expression for time period in terms of density of the planet. So based on this, if we consider that two planets are there which are having same mean density, and there are two satellites which are revolving around them. So since these two planets are having same mean density, the two satellites which are at the same heights will revolve with the same time period. Based on this condition, time period is inversely proportional to square root of density. Based on that, here we can represent that as the two planets are having same mean density, the satellites which are revolving around the two planets at the same height, they possess the same time period. Now let's observe this angular momentum of a satellite. We know that angular momentum is represented as mv0r, where r is the distance of the satellite from the center of the planet, and we know that v0 is equals to under root of gm by r. So in the place of v0 we can substitute this value. As we substitute, the angular momentum is represented as L is equals to m into under root of g capital M by r into r. As we bring this r into the square root as well as m, then angular momentum can be represented as g capital M square r square by r, where one r gets cancelled. Then L is equals to g capital M square into r. Sure. Observe the relation. Small g is equals to capital G capital M by r square. So in the place of capital G capital M, we can substitute g r square. As we substitute, angular momentum can be represented as g r square M square into r. M square into r. So this represents the angular momentum of a satellite which is revolving around the earth. Suppose if we consider the height of the satellite is negligible as considered to radius of the earth, then so this h can be neglected. Then in the place of small r we can substitute capital R. As a substitute, the angular momentum can be given as L is equals to g r square M square into r, nothing but it can be represented as g r cube into M square. This represents the angular momentum of a satellite when it is revolving very near to the earth. Take a screenshot, we'll continue. Now we are going to discuss about energy of a satellite. Come to the case. Here we consider our Earth or any planet with a radius r, and a satellite is revolving around the Earth at a height h, at this height. So as you observe that when the satellite is revolving at this height, and if we consider from the center of the Earth, if the satellite is at a distance of r, we know that small r equals to capital R plus small h. Now here, as the since the satellite is placed at this point and it is revolving, it possesses a potential energy at this point. Potential energy at this point, and here the potential energy of the satellite is given as minus g m e m suffix e, where m suffix e is nothing but mass of the Earth small m by r, where small m is nothing but mass of the satellite and m suffix e is nothing but mass of the Earth. So here we had represented the potential energy of the satellite. Why? Because the satellite is placed at a height h from the surface of the Earth. So that we had represented the potential energy of the satellite. Now, since the satellite is moving with the velocity v0, this satellite possesses kinetic energy. Why? Because it is moving around the planet with constant speed. Whereas the kinetic energy of the satellite is given as half m v naught square, half m v square. But we know that v naught is equals to under root of g m suffix e by r. So as we square this expression, v naught square is equals to g capital M suffix e by r. So in the place of v naught square, we can substitute g capital M suffix e by r. As we substitute here, the kinetic energy can be given as half m into g capital M suffix e by r. So the expression can be represented as half g capital M suffix e small m by r. So this represents kinetic energy of the satellite as well as potential energy of the satellite. Based on this, now we have to represent a total energy, and we know that total energy is given as the sum of potential energy and kinetic energy, where potential energy is minus g capital M suffix e small m by r plus 1 by 2 g m suffix e small m by r. Observe that we can take a g m suffix e m by r as common. As we take a g m suffix e m by r as common, here 1 by 2 minus 1 is left. 1 by 2 minus 1. 1 minus 1 by 2, nothing but 1 by 2. So here we get a minus sign. Then a total energy can be represented as a minus 1 by 2 g capital M suffix e small m by r. This represents the total energy of the satellite possessed at this point. Here we had represented the potential energy of the satellite, kinetic energy of the satellite, and the total energy. The ratio of potential energy is to kinetic energy is to total energy is given as minus g capital M suffix e m by r is to 1 by 2 is to g capital M suffix e small m by r is to minus 1 by 2 g capital M suffix e small m by r. On doing LCM, the ratio is represented as minus 2 is to 1 is to minus 1 is to minus 1, minus 2 is to 1 is to minus 1. Suppose if we consider a satellite jumps from lower orbit to higher orbit. So initially the satellite is at this position. If it jumps from this orbit to this orbit, from this orbit to this orbit, then its height has been increased from h to h dash, then its potential energy increases. Potential energy increases, where its kinetic energy decreases, then its total energy increases. And next its linear momentum decreases. Angular momentum increases when a satellite jumps from lower orbit to higher orbit. Suppose if the same satellite jumps from higher orbit to lower orbit, then its potential energy decreases. Kinetic energy increases. Then total energy decreases. Linear momentum increases, and angular momentum decreases. As well as we can also consider the speed along with this. So in this case the speed decreases. Since it has jumped to higher orbit, speed decreases, whereas in this case speed increases. So when a satellite jumps from higher orbit to lower orbit, then its potential energy decreases, kinetic energy increases, total energy decreases, linear momentum increases, angular momentum decreases, and speed increases. It's a speed increase. Means as the satellite comes very near to the planet or earth, it starts revolving around the earth with more speed. As it moves away from the earth surface, its speed decreases. It slowly moves around the earth. Here, as you observe the total energy of the satellite, it is represented as minus 1 by 2 g m suffix m by r. If we supply this amount of energy to the satellite, means total energy possessed by the satellite is represented as it's a requirement of the energy, minus 1 by 2 g m suffix m by r. It is in the negative sign. If we give positive amount of energy to that satellite, its total energy becomes 0. Then this satellite moves away from the earth surface and now return back. If its total energy becomes, means if we supply same amount of energy in positive way, the satellite moves away and now return back. So take a screenshot. We'll continue. Now we are going to discuss about geostationary satellite. If we consider this plate as earth, and if we consider this marker as a satellite. So as the earth rotates from west to east, with respect to the rotation of the earth, the satellite also moves. So here the angular speed possessed by the earth is equals to the angular speed possessed by this satellite. So when we view this satellite, it continuously appears with respect to earth. At morning time, when we observe, the satellite will appear at this position. As the earth rotates, again with respect to the rotation of the earth, the satellite comes to this position. And if the earth rotates at evening time, it comes to this location. Means it continuously moves with respect to earth. It appears stationary. That's why it is known as a geostationary satellite. With respect to earth, the satellite appears stationary. Means the orbital speed possessed by the earth is equals to the orbital speed possessed by the satellite, which is revolving around the earth. So the time period of revolution of the satellite is represented as 24 hours. Why? Because it appears stationary. It appears stationary and it continuously moves with respect to Earth's orbital speed. Whereas the orbital speed of the satellite is represented as 3.1 kilometer per hour. 3.1 kilometer per hour. This is the orbital speed possessed by the satellite. And in order to appear stationary, the satellite has to be placed at a height of h from the surface of the earth, where h is given as 35,600 kilometers. 35,600 kilometers. At this location, if we place the satellite, it appears stationary. Whereas the time period of revolution is equals to time period of rotation of the earth. That's why also we can also represent it as a geostationary satellites. Whereas we can also consider these geostationary satellites as the parking satellites. Parking satellite. You can also call it as a parking satellites. Why? Because it appears as stationary when it is. Whereas these geostationary satellites are placed along the equatorial line along the earth, so that they appear constantly along the equatorial line. These geostationary satellites are used for sending and receiving the TV signals, as well as for communication purpose. Communication purposes. They are also useful for GPS, global positioning system. In this way, these geostationary satellites are useful to us. Now we are going to discuss about polar satellites. These polar satellites move from one pole to another pole, from north pole to south pole and south pole to north pole, continuously along the vertical line like this. They continuously move like this around the earth, so that since the satellites are moving from one pole to another pole, they are called as polar satellites. They are called as polar satellites. After that, these polar satellites move within a very short interval of time, as compared to geostationary satellites. These geostationary satellites require 24 hours, whereas polar satellites move with a very small interval time, just like 84.6 minutes. Means they are placed at very low height. Since they are placed at very low height, easily they can complete the revolution within this time. One revolution within this time. So what are the uses of these polar satellites? Means these polar satellites are used for verifying atmospheric conditions. And also in order to verify the raw materials present on the surface of the earth, and in order to photograph, if a camera is placed on this polar satellite, then we can take the photograph of the earth like this when it is available. Why? Because if we consider initially the satellite is at this position, as it starts moving in this orbit, the earth will be rotated. As it rotates, initially it takes photo at this location. Again, as it starts rotating, this rotation will change like this. Means orbit. In this way, as the satellite moves in the downward direction, the earth starts moving. So we can take the photograph in a vertical plane. In this way, we can take the total earth's photograph. We can take the photograph of a total earth. So in order to represent the atmospheric conditions, as well as in order to represent the raw materials present on the surface of the earth, as well as it can also be used as a spy to our country. In this way, these polar satellites are very useful to us. Take a screenshot. We'll continue. Let's solve a numerical based on this concept. Observe this: an astronaut orbiting in a spaceship around the earth has a centripetal acceleration 2.45 meter per second square. Find the height of the spaceship, where r is the radius of the earth and it is represented as 6400 kilometers. So here we consider earth with the radius r and a satellite at a height h from the surface of the earth. Now we have to represent this height, where the centripetal acceleration of this satellite is given as a suffix sequence 2.45 meter per second square. Now here we have to represent the expression centripetal acceleration in terms of gravity, where we know that centripetal acceleration A is equals G capital M by R, because we know the relation for small g and capital G, as a small g is equals gm by r square. So where r is the distance of the satellite from the center of the earth, small r is equals to capital R plus small h, small r equals capital R plus small h. So as you substitute this value, you observe that g capital M by r plus h whole square, and we know the relation between small g and capital G as a gm by r square. This is the relation given on the surface of the earth, whereas here we had represented the relation at a height h, A is equals to gm by r square. From this here g capital M is equals to g r square. So in the place of gm we can substitute g r square. As we substitute A is equals to g r square by r plus h whole square. So as we bring this g towards this side, here A by g can be represented as r by r plus h whole square. Now we have to represent the value of A by G, where A is equals to 2.45 meter per second square, and we know the value of G as 9.8 meter per second square. So as we substitute these values, A by G can be given as 2.45 by 9.8. After that 2.45 4 times, here we get 9.8, then A by G is equals to 1 by 4. So in the place of A by G we can substitute 1 by 4. As we substitute, observe that r by r plus h is square equals to 1 by 4. Let's apply square root on both sides. As we apply square root on both sides, r by r plus h is equals to 1 by 2. Let's cross multiply this expression. R plus h is equals to 2r. R plus h equals to 2r. So bring this r towards this side. Then 2r minus r is equals to h. 2r minus r is r. R is equals to h. Nothing but h is equals to r, where r is 6400 kilometers. So the satellite has to be placed at a height of 6400 kilometers. Take a screenshot. I hope that you had liked my video. Please give a like to this video, share this video to your friends, and don't forget to subscribe my channel.